In a stable dynamical system, every nearby trajectory eventually settles. If you drop a particle within a boundary, local forces pull it into a central equilibrium point, spiraling inward until it comes to rest. That changes when we introduce a new variable into the ODTBT field equations, the lock potential. This phase space diagram plots delta phi on the horizontal axis and r on the vertical. As the lock potential activates, the geographic boundary of the safe capture zone shrinks inward. This is basin contraction. Because the boundary has moved, trajectories that would have previously spiraled down to the center are now left outside the safe zone, leaking out through a specific geometric sector. This geometric shift represents a distinct vulnerability, reducing the amount of ambient noise required to knock a trajectory off course and force an escape. Physicists measure this specific vulnerability using the Transport Obstruction Index, denoted as ρL. It calculates the ratio of the critical noise amplitude required for escape when the lock potential is active, compared to the baseline system. Looking at the published ODTBT source abstract, we see the central result of the campaign. The lock potential reduces the critical noise threshold required for escape by 16.2. They built a native CUDA implementation from scratch, running on an NVIDIA Grace Blackwell GPU. This compares the two integration methods. Python used an 8th-order adaptive solver, mapping the curve with variable steps. The CUDA code uses a 4th-order solver, forcing fixed-length intervals. Forcing equations through opposing mathematical filters is the ultimate stress test for structural agreement. The CUDA validation returned a new ρL value of 0.8417. That is a 0.46% difference from the original published metric. That microscopic variance is exactly the mathematical expectation for a local truncation error when running a 4th-order integration method over 200,000 discrete steps. Because the noise threshold shift survived a complete overhaul of both the hardware architecture and the mathematical integration method, the basin contraction is verified as a physical reality. While the core metric survived, the translation audit exposed hidden numerical traps in how the simulation recorded data. The first trap involved counting transitions across a specific phase space boundary, known as shell crossings. The original Python code counted 35 crossings. The initial CUDA run counted 41. This timeline illustrates the misaligned observation phases. The CUDA solver included a 1,000-step transient phase, entirely missing the initial spiral-in distance. Realigning the window to time 0 instantly restored the correct metrics and matched published behaviors. The remaining gap of 6 shell crossings is a byproduct of how fixed-step RK4 solvers discretize the exact same curve differently than adaptive DOP 853 solvers. Both values are correct for their respective integration methods. When high-level physics simulations disagree on secondary metrics, it is often a matter of boundary definitions, demanding canonical conventions to ensure future results are comparable. The second major audit finding revealed a critical error regarding parameter definitions during the noise bisection search loops. This equation defines the damping coefficient. It relies on sigma hat, representing noise amplitude. Because the simulation adjusts noise, sigma hat actively updates. However, CUDA developers incorrectly hard-coded it to 0.1. This made the coefficient 42 times too large, causing artificial overdamping and suppressing escape trajectories. A rigorous audit of the original Python codebase proved the initial researchers avoided this trap. They correctly coded the dynamic formula, recalculating the parameter at every step, and fully validating their published results. Freezing a variable that physically must scale with systemic noise will artificially suppress the exact escape behaviors the model is designed to measure. Now that the independent implementations have converged within acceptable numerical tolerances, we can look at what the validated math reveals about the system's nature. To prove that the boundaries of a basin are permanent structural features, physicists test for horizon independence. This chart plots the critical noise thresholds across two drastically different observation timeframes, t equals 1,000 and t equals 2,000. Extending the integration timeframe results in a perfectly flat line. There is exactly 0% drift in the critical noise threshold between the two horizons. If giving the system twice as much time does not change the escape threshold, the escape is not caused by a slow, accumulating instability. The trajectories are hitting a permanent structural wall built directly into the field equations. To see that structure, the Phase 2 CUDA campaign leveraged the GPU's processing power to map a massive grid of 1 million distinct initial conditions. Across that entire grid, the lock potential causes a 66.2% volumetric contraction of the entire basin. This phase space map plots the results. The 66% contraction is not a uniform shrinking. It manifests as the opening of a single dominant 90-degree escape sector, spanning from -75 to +15 degrees. By calculating the Jacobian eigenvalues at the equilibrium point, -0.5 plus or minus 1.57i, we confirm that the center itself remains a stable spiral. The local stable manifold points strictly along a -6.5 degree axis. But the massive escape corridor blasts out at -60 degrees. The two geometric features ignore each other completely. The core stability hasn't degraded. Instead, the global topology of the phase space has reorganized to create an exit. The lock potential restructures the global geometry of the system. In dynamical systems, escape is often just a matter of uncovering the hidden architecture.